Welcome back. This is the fourth and final part of the statics review. We'll do one final example. If you felt comfortable with the previous examples, you might choose to skip this one. In this problem, we look at a rigid bar which is supported by a pin support at the end and a rod CE which acts in tension. And the question that we're asked is, what is the tensile force in member CE and what is the most direct way to find it? This illustrates that we don't necessarily always have to work from beginning to end. Sometimes we can take a clever approach to simplify the problem and get directly at the information that we're looking for. This is a statically determinate system. As before, we'll start by drawing a free body diagram of the system. I'm going to draw that rigid bar right below the original. I just want to draw in the loads, the 10 kip acting downward, 20 kip acting downward at point D. I'll go ahead and not show the lengths because they're illustrated directly above. I know that at point C I have a tensile force in member CE, which I'll call TCE, acting in the diagonal direction. And I also know that I have unknown reactions, A sub x and A sub y at support A. Okay? It also might help me to consider this problem to dissect the components of TCE. So I'm going to do this a little bit more clearly over here. Okay, my tensile force acts in the diagonal direction. According to the geometry, this unit of length is 12 feet. The unit of length in the vertical direction is 9 feet. We again recognize this is a 3, 4, 5 triangle, making the diagonal length 15 feet. Okay, we might also recognize, and we'll see why in a minute, that we can break this down into components in the vertical direction and the horizontal direction. Okay, so what is the most direct way to solve for the TCE? The best way is by summing moments about point A. Again, for the reason that A sub x and A sub y will drop out of that equation and we can solve directly for our unknown. We don't even need to evaluate the reactions at A in order to do so. So let's go ahead and do that. The sum of the moments about A equal to 0. We're going to assume moments positive in the counterclockwise direction, and we'll add up the contributions. Okay? What is the contribution to the tension? The contribution of the tension in bar CE to the moment about A. Well, the component in the x direction does not contribute at all because its line of action is through point A. Only the component in the y direction contributes. That component, according to our geometry over here, would be 9/15 of the total tension, TCE. Okay, that's the force. That's just the component of the force. Multiply that by the length or the moment arm, which is 12 feet, because the point C is 12 feet from point A. So 12 feet, that's our distance. What else causes a moment about point A? The 10 kip load in the negative direction, because it's acting clockwise, and its distance is 8 feet. Also, the 20 kip load, negative, because it's acting clockwise, and its distance is 16 feet. Notice that each of these terms is a force times a distance. Force times a distance, and we keep track of units the whole way through. Set that equal to 0, okay, and now we can solve for TCE. TCE equals, bring these terms to the right hand side, reverse their sign. 10 times 8 is 80. 20 times 16 is 320. So on the top, 80 plus 320 kip feet. Divide that by 9/15 times 12 feet. Feet cancel out, and we are left with 400 over 9/15 times 12. The whole thing reduces to 55.6 kips, and it's positive, so it is in fact a tensile force. And that is our direct way of going about the answer. And it does make sense if we do a quick logic check. The tensile force larger in magnitude because it's in the diagonal direction, balancing out these two forces that are pulling the bar downward.